So for the first one here, we're adding. Remember, when we add or subtract, we must have same name. And in scientific notation, that comes down to that power of 10. They are both 10 to the negative 13th. So we combine the count. 7.2 plus 9.4 is 16.6. And we keep the same name. This has to be adjusted, however, because we have to move the decimal point. There's only one digit in front of the decimal point. Yep, so that becomes 10 to the negative 12. Yep. Over here, we're subtracting. We do have the same name, both 10 to the 11th. So 6.38 minus 5.84 is 0.54 times 10 to the 11th. And then we make that 5.4. Yep, number got bigger, so the power gets smaller. So 11 minus 1 is 10. So 5.4 times 10 to the 10th. Multiplying or dividing, we do not need the same name. We are going to combine the count. 6.3 times 4.5 is 28.35. We also combine the names. 10 to the negative 8 times 10 to the 15 is, we multiply exponents with the same base, we add the powers. So yes, negative 8 plus 15 is 7. However, we do have to adjust. Perfect. Number gets smaller, power gets bigger. 10 to the 8. Dividing. 7.2 times 10 to the negative 11, or 10 to the positive 11th, divided by 1.08 times 10 to the negative 6th. We divide the count. 7.2 divided by 1.08. 6.67, we'll round it to. Here's 66666. Yep. Times 10 to the, yeah, when we divide, we are subtracting powers. 11 minus the negative 6 is 11 plus 6, or 17. Exponents. Well, we start out, we take the count to the power of 3. 2.7 to the power of 3 is, oh, gotcha. Well, 2.7 to the power of 3, 19.683, times 10 to the, well, the negative 9 to the power of 3 is negative 27. When you got an exponent to another power, you multiply the powers. This becomes 1.9683 times 10 to the 26. Number got smaller, so the power gets bigger by 1, so we add 1 to it. Over here, fourth root. We take the fourth root of the number. Fourth root of 2.8561 is 1.3. On your calculators, all your calculators are different, but most of you will actually have an X root or an N root key that's above your power key. So you would type in 4. Now on my calculator, I go through a menu, select the X root, and then I put in the 2.8561. So I had to type in that 4 first to tell it that it's a fourth root. Then what do I do with my power of 10 here? 10 to the 28th, the fourth root. When I'm doing a root of an exponent, I divide the power. So like here I multiplied the power. Here I'm going backwards. I divide the power. 28 divided by 4, 7. So 1.3 times 10 to the 7th. What do you guys think? So you had 2.7 times negative 9. So let's do this. On my calculator, I'm going to do this. 2.7. I'm going to put it in a scientific notation. That EE key is your scientific notation. I'm going to hit enter, and then I'm going to go to the power of, what was it, 3? I'm getting negative 26. On your calculator, if you do this, if you do 2.7 times 10 to the negative 9, you have to hit enter first and then do the power of 3. Otherwise, it does some messy things. Okay. Sure. Okay, well, the good news is we're done with scientific notation in about 15 minutes. The bad news, you have a... Okay, so time to take a look at some new material here. Does anybody need a second to get the extra credit questions down yet? Okay. So we want to talk more about these algebraic numbers. Now remember, the algebraic numbers are just where we have names that are the variables. You know, like 7x or 4x to the third. Those are algebraic numbers. I want to take a little bit of time now that we've done the scientific notation to review the concept of place value. What we have is called a decimal number system. Decimal is another word for base 10. And what that means is our place values are based off of the number 10. And what they're really based off of is an exponent. Remember, an exponent has two parts to it. It has the power, but then it has a base. This part of it is the base. So base 10 numbers are numbers that the place values are based on exponents with a base of 10 in the exponents. Then all the powers vary. So you hear about binary numbers or octal numbers or hexadecimal numbers. That's actually a numbering system where the place values have a different base, different number in there as the base. Binary, it's a 2 in there as the base of the exponent. So anyway, we have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, as we saw over the last couple of days with our scientific notation. If I have a number like 2,836, I can write that out. We've looked at this way back at the beginning of the semester as being 2,000s and 800s and 3 10s and 6 1s. Well, another way we could have written that a little bit shorter would have been 2 times 10 to the third plus 8 times 10 squared plus 3 times 10 to the 1, we can just leave it as 10, plus 6 times 10 to the 0, we just often leave that as 6, but it is 6 1s. Well, with that written out like this, I'm going to draw your attention to a similarity between that and an algebraic number. Bless you. Do you see the similarities here? 10 to the third, x to the third. 10 to the second, x to the second. 10x. Nothing, nothing. Algebraic numbers really are just like our whole numbers, except the place values, instead of being powers of 10, are now powers of x. So instead of the 10 to the third or thousands and 10 squareds and 10s and 1s, it's x to the thirds and x squareds and x's and 1s. Because anything to the power of 0 is 1. So no matter what base or numbering system is, that last digit's always going to be the 1. Now, there are a couple of differences in our algebraic numbers. In our decimal numbers, what is the largest number that can be there? Well, the largest number that any digit can be, 9, right? Because if it gets any bigger than 9, you have to carry it over the next place value. Well, in our algebraic numbers, there isn't a carrying like that. So we could have 7x to the third plus 13x squared plus 27x plus 5. We can have digits bigger than 9 in our algebraic numbers. The other big difference comes with negatives. In our integers, if I have a negative 239, that means every digit is negative. That's a negative 2 hundreds and a negative 3 tens and a negative 9 ones. In an algebraic number, each digit is free to be positive or negative on its own. I can have 7x squared and a negative 11x and a positive 9 ones. So there are some subtle differences. Basically, the algebraic numbers are a lot freer because they're not restricted by some of the restrictions of base 10. So when we start to do operations with these algebraic numbers, they're going to follow the same rules as we did with our whole numbers. If I have 5 inches plus 7 pounds plus 3 inches plus 13 pounds, what can I combine there? The like names. The 5 inches and the 3 inches make 8 inches. 7 pounds and 13 pounds make 20 pounds. Likewise, I could have 5x plus 9y plus 18x plus 6y. What can I combine here? Yeah, the 5x and 18x make 23x. 9y and 6y make 15y. Now notice up here I put that plus in there as kind of an and. Same thing here. That's a positive 15y, so I put a plus in there. Now, one of the differences is these, inches and pounds are pretty much going to be positive numbers. With our algebraic numbers, we can throw in negatives. I could have 7a minus 14b minus 13a plus 9b. So I'm going to combine here. 7a and negative 13a make negative 6a. Negative 14b and positive 9b, negative 5b. So the negative just becomes what attaches. I put it in there. The negative, the symbol here goes with the number that comes after it, like we talked about with subtraction before. Since it's a negative 5, we just put it as minus 5. Or we could have, if we wanted to, made it negative 6a plus a negative 5b. That is, they both mean the same thing. Can I combine that and make 21 inches to the third or 21 inches to the fourth or whatever? I gotta be careful. Can I combine 7 inches and 11 inches squared? They have different names. I cannot add them. But I can combine the 7 inches with the 3 inches, gives me 10 inches, and then I have plus the 11 inches squared. Normally, we would do it the 11 inches squared first. The reason we do that is it's a math grammar thing called descending order. I'm spelling that horribly, I'm sure, but descending order where you put, just like our place values, we have 10 squared comes before 10 to the first. An x squared comes before x to the first. Same thing here. The inches squared comes before inches to the first. Just regular inches. Yes. And inches, obviously in the physical world, you have inches are length, inches squared are areas, surfaces, inches cubed are volumes, or they're solids. Inches to the fourth physically don't exist, but it actually is a unit when you get into like structural engineering and stuff. It's like your moments that describes how things bend and stuff like that. But there is no visual representation of it. It's a theoretical unit. It describes a property of a material or structure. Well, let's go to the next step. What if we have 5x squared plus 7x plus 11? Again, just like our scientific notation, I'm putting in parentheses not because there's something we need to do there. I'm just separating that out as a number. Plus 2x squared plus 9x plus 3. If I'm asked to add those two numbers, I can add them just like whole numbers. Because remember, these are just the place values. So let's write out the 5x squared plus 7x plus 11. Now I have to line up my place values. The x squared, the 2x squared goes under the other x squared. 9x goes under the 7x. And the 3 ones goes under the 11 ones. And I have to remember I am adding here. And I don't have to start on the right and work my way back to the left, but I will just because that's what we're used to. 11 plus 3, 14. It's positive, so I'm going to put a plus in front of it. 7x plus 9x, 16x. Again, positive, I'll put a plus in front of it. 5x squared plus 2x squared, 7x squared. Now it's positive, but I don't have to put a plus in front of it because there's nothing up here that I need to connect it to. Now, as we said, digits can be positive or negative all on their own. So we can have 3x squared minus 19x plus 7 plus negative 5x squared plus 11x minus 3. So I'm still going to set this up just like I would dealing with whole numbers. We are adding 7 plus negative 3, positive 4. So you're going to put a plus in front of it. Negative 19x plus 11x, negative 8x. Now that negative becomes a minus that links it to the next term. 3x squared plus 5x squared, or negative 5x squared, negative 2x squared. So addition's actually relatively simple. Where it becomes more complicated is when we subtract. And at the surface, subtraction is no more difficult than that. Bless you. So we've got something like this, 3x squared plus 19x plus 2. And just like addition, we must have the same name to subtract. So I line up my place values. But we are subtracting down the columns. 2 minus 7, negative 5. Again, that negative becomes a minus that connects it to the next term. 19x minus 8x, 11x. And since it's positive, we'll put a plus there to connect it. 3x squared minus 7x squared, negative 4x squared. So that wasn't so bad. But where it becomes more difficult with the subtraction is when we throw in stuff like this. So I'm going to drop down here one ways. And we have to remember we are subtracting. So 7 minus a negative 8. 7 minus a negative 8 is 7 plus 8, right? So it is positive 15. Negative 9 minus 13. Notice I'm writing them off to the side. I tend to do that so I can keep track. So it becomes negative 9 plus a negative 13, which is negative 22x. 5 minus 3, we can do that one. 2x squared. Okay, we've only got about 8 minutes left, so I'm going to let you guys have some time to practice. We'll talk about multiplication and division tomorrow. This is in the big book. Page 333, exercise 13-2. And page 335 through 336, exercise 13-3.